do you end up with the same clustering depending on where you start, and is it guaranteed to converge? To answer those questions, you need to think about what it is that this procedure is actually optimizing. Right? Because just grouping points, there's no objective function associated with it. So what it is doing is it's trying to minimize the aggregate distance from each centroid to the instances that are assigned to the centroid. So you could think of it as the square distance between the centroid and a data point summed up over all the data points assigned to cluster J, and then summed up over all cluster centroids J. So it's intra-cluster distance. It's the distance within the clusters. You don't care about the distance between the clusters. This method doesn't. Other methods do. So one way to interpret it is you can interpret it as variance, right? So remember, the square of Euclidean distance is pretty much the same thing as the variance. So what you're computing here is you're computing the variance inside the groups. So that's what you're trying to maximize. The procedure does converge. So if you run it from a fixed iteration, it will get to a point where which is a stable point, and from that point it is not going to move. So in that sense, it converges, but it does converge to a local optimum. So a local minimum of the variance. What that means is if you start with a different initial configuration, you will end up with a different result. You will end up with different centroids and different cluster memberships. So it is sensitive to where you start. It will always converge, but it will always converge to a different place when you start from different initializations. So what do you do in practice? If you can afford it, if your data set is small enough, or if your computing infrastructure is large enough, you run the procedure several times. So you instantiate a different set of k centroids randomly in space. You run the k-means algorithm, then a different set, run k-means, different set, run k-means. For every single clustering, in the end, you will have an aggregate distance. So you'll have a number that tells you how close the points are to their cluster centroids. And that number will be different for various initializations of the algorithms. So what you do is you pick the clustering that gives you the smallest distance, the smallest variance. Basically, you're looking for the tightest possible clustering of the data, the tightest in the sense that all the points are pretty close to their centroid, as close as you can possibly get. That, of course, can be done only if your computing infrastructure allows it. On many real-world data sets, your data set it's so large that you can't even run k-means to convergence once. You end up running it for like 10 iterations and then stop, because that's already taken a month. So you're not gonna run it for more. Question? How will it classify a point? It does not classify points. Okay, so if there's a point an equal distance from both centroids, you are very unlikely to get something like that. If it does happen, you need a tiebreaker. So you need some rule that will break ties for you. And what rule you use is inconsequential, because unless you're dealing with discrete data, it's not going to happen very often. Okay, now one really interesting thing about k-means, it seems like a very nice and sensible technique, but it does have some annoying properties. One of these annoying properties is if you have 2 points that were nearby in the data, they are not guaranteed to end up in the same cluster. So, for example, if you have a data set with 4 points, like that, you would like these 2 points to end up with one cluster and those 2 points to end up in another cluster. Right? Now that is not always going to happen with k-means. So if you happen to have centroids set as follows, so that's your red centroid and that's your yellow centroid, that is a stable configuration, and k-means is not going to get out of that configuration. So what it's saying is that the 2 points at the top, that's one cluster, the 2 points at the bottom is another cluster. And that's a stable configuration. The means are not going to move in this case, and the points are not going to change colors, because this yellow point, it's actually closer to this yellow centroid than it is to the red centroid. So that is a local minimum, and it will never ever get out of that local minimum. And such local minima come up surprisingly often. So you do k-means, you expect all the points to sort of be similar to each other, but you will find lots and lots of examples where nearby points are in two different clusters. That's not a property that k-means is designed to preserve. When we talk about agglomerative clustering, those algorithms preserve this property. So there, you're guaranteed that two nearby points are going to end up in the same cluster. For k-means, you don't have that guarantee.